Okay,
Okay.
this is David Zierler, director of the Caltech Heritage Project. It's Thursday, June 15th, 2023. I'm delighted to be here with Dr. Erik Ivins. Erik, it's so nice to be with you. Thank you for joining me today.
Thank you, David.
Erik, to start, would you please tell me your current or most recent title and institutional affiliation?
I formally retired from JPL on February 5th of 2022. So it's been a little bit more than a year that I've been retired. Although I'm not a fully retired employee, I retired as a senior research scientist, which allows me to stay on as a research associate, which means that I don't get salary, but I get all the full privileges of a person with a badge and all the access to the library, access to VPN, and all the electronic services that JPL can provide. And I continue to do research. I continue to, most importantly, advise younger scientists at JPL. So I'm still traveling for JPL. I'll be going to Berlin to the IUGG meeting in July. So I'm still an active scientist reviewing papers and so on. But I don't have anybody who gives me deadlines, so to speak.
Erik, what's the kind of research that has compelled you to remain active? What's interesting to you in the field?
Oh, I would say that one of the interesting things is the reconstruction of the lake quaternary, which means basically looking at how both life forms and topography and the water system has evolved over the last million years or so. I think that's one of the things that I'm just happen to be reviewing a paper where that was the discussion. So that brings me to that particular topic. I would also say that I've always been interested in mantle geophysics in all of its aspects. And since I'm at an institution that does planetary science, that would include why planetary orbits become circularized through dissipative interaction in the mantle itself or within water systems. And that brings me to, probably the topic that I'm most active recently, and that is the constitutive nature of solid Earth and how creep phenomenon occur in ceramic materials, and how the experiments that are in that field can be translated into geodynamic models of data that we observe in geodesy.
Erik, given that you are serving now in a mentor capacity at the senior stage of your career, when you look at some of the things the upcoming generation are interested in, what kind of window does that provide into where the research is headed?
Oh, I would say that it's in the modeling realm. It's the fact that we're looking at computational capabilities that we had not conceived of 25 years ago. I mean, we're now talking about, I'd say 25 years ago in my career, if we were talking about doing 100 simulations, that seemed like sufficient to come to conclusions about what model parameters were and so on. But I think today we see ourselves moving to computing millions of model simulations, and then looking at the nature in which the parameters vary and how the data sets that we use are capable of being able to say anything. And it's sort of interesting. This brings up to this direction of artificial intelligence, and you can almost see this field kind of breaking open and having its growing pains, because you can see some young scientists have gone a bit too far with this, and not really being able to grapple with the processes that are involved in each of the links that a simulation code will give you versus the data constraints that you might have. If you have any of these things slightly mismatched, you will wind up with a solution that has used 100 million solutions, but it may be the wrong solution. And so I think we have to understand that we really have to scrutinize what we get out of that kind of science.
With all of this computational power, with what AI can do, beyond what it can't do, what are some of the top line items that we now know that weren't possible, as you say, 20 or 30 years ago?
Well, if you look at remote sensing from space, we're now capable of being able to look at images of ice sheets or even smaller ice systems, and we can see how they flow in time. We can do this by looking at speckle tracking, and that kind of data set simply was not available at the dawn of the era of remote ice sheet sensing, which really goes back into the 1980s and was led by people who are now long retired.
Erik, to get a sense of your research expertise from the broadest to the specific levels, what is the umbrella discipline that would cover everything that you do? And then when you get right down to the panels that you would sit on or the journals that you would publish in, what would you call yourself in that context?
That's kind of a difficult thing to say because I'm pretty interdisciplinarian. I would say the specific topic that I would always be kind of brought to the table on in terms of forming small working groups and so on is the interaction of um, the cryosphere and the solid Earth. And this can come about in many ways. For example, one of the ways it can come about is the formation of landforms. During the glacial age, you get outwashes from the melt, and that changes the topography. That's not so much what I'm interested in. It's more the fact that the stress at the surface of the Earth changes dramatically at a level that can create large earthquakes. And it's that stress level that then induces flow in the mantle. And since the glacial age is a global phenomenon that involves 130 meters of sea level change, it affects all aspects of the solid Earth, including the core. And as a consequence, it's a global phenomenon that can be recorded today in changes of the Earth's gravity field, and also of changes in the long-term rate at which the pole moves through the crust of the Earth. So that's the larger context of having the link between smaller glacial systems like Patagonia, where the same phenomenon occurs on a small scale, and a very large scale where one has to have an expertise in satellite gravity. So that's kind of the niche that I'm in, is that I have expertise in geodesy such that I can make this link between ongoing sea level rise, for example, and the gravity field of the Earth. That's really kind of and if you combine that with the fact that I'm an expert in how the mantle also participates in this process and produces a gravity field, then that's my unique niche in the science world.
Erik, when scientists started to ring the alarm bells about global warming in the late 80s and early 90s, did that affect your research agenda, and how did that affect cryospheric research in general?
Yeah, so in December of 1984, I read a paper by Mark Meyer, who made a inference from what he understood was glacial mass balance during the 20th century and 20th century sea level rise, and also the hypothesis that carbon to these phenomena, decrease of glacial mass and the rise in sea level. And he made a quantitative statement about what the rates were of all of the large glacial systems in the Earth. And at that time, we thought both Antarctica and Greenland were stable. So these became the sources, the known sources. And Mark Meyer actually was a former Caltech um, a glaciologist. There weren't too many of them back in the 1950s and 1960s, but he was one of the people who organized field campaigns to do observations of major glacial systems. So in his late part of his career, he published this paper in Science. I got a very early copy of this. And together with a colleague, more senior colleague at JPL, we put together a gravity field based upon his estimates of the global glacial loss rates. And we were able to show that this was a fairly large effect on a satellite system that we already had in place. There was a French satellite and a US satellite that were very high orbit, and they were very sensitive to the change in the shape of the Earth's gravity field at very large scales. And this was the trigger point for my involvement in what we might call climate science. So it was fairly early on, and I've kind of honed that area of expertise. I didn't see a responsibility to publish so much in it as to keep the computations going, because they were relevant to our Legios investigator program, of which I was a member.
Eric, of course, understanding climate change is extraordinarily complex. There's so many scientific disciplines that are required to understand these trend lines. Where does someone with your expertise add to what we really understand to minimize the uncertainties, to minimize the error bars?
So I would say that one of the, if you look at what's required to move the mantle around, it requires very long time scales. Because the viscosity of the mantle is so high. So we're talking about climate changes that are on the order of 5 million years. I mean, we actually need a 5 million year simulation to be able to predict the correct direction and magnitude of the secular position of the pole as it changes in time, because the viscosity of the Earth is controlling the redistribution of the moments of inertia of the planet. And so this viscous timescale forces us to understand in intimate detail what the changes were in the hydrology of the Earth going back 5 million years. So we begin to understand how rapidly sea level can change, for example. And so when we're confronted with someone who's a little bit skeptical about, well, how do we know that sea level doesn't always change as rapidly as we're currently seeing it? By having an understanding of the rates at which sea level changed when we went from a glacial environment globally to an interglacial, helps put current changes in the context. For example, we now know from geological observations globally that for the last 5,000 years, we've not seen any sea level changes that are even 100th of the rate that we're seeing them now. So that's a pretty profound, very quantitative fact that we're knowledgeable of. So it may not necessarily be something where we have a bell-shaped curve that we can move around and say, well, here's what the statistics are. But we know in an order of magnitude sense what we are facing right now with ongoing climate change.
Eric, a question sort of like the road not traveled. Do you think that if you had taken an academic path, if you had become a professor, would you more or less have studied the same things that you've pursued at JPL? Or how central is the mission to JPL in driving the things that you've worked on?
Oh, I think it's absolutely essential, because I think in academia, one of the things, I mean, and I could see myself in going down the academic path, and I think I'd be perfectly happy there. That when you're in an academic institution, you really are trying to adjust the research that you have by the opportunities that you have to receive research funds, and also the resources that you have from the institution that allow you to have quality graduate students that can pursue these things. And as a consequence, you may be going from working on a particular area, say working in the mantle or working in geomorphology, that's fundable for the current time, and you have graduate students that work on those. Whereas working within NASA and JPL, you have space, you have what the engineers call metal in the sky. And that metal in the sky determines, and the capabilities of those instruments on those spacecraft determine the time span over which you dedicate your research career. And so it's difficult to get a student involved in a particular spacecraft program because their life cycle of their career is probably going to be, their changes in their career are going to be shorter than the time span over which that instrument in space is collecting information. So I think scientists at JPL tend to have research continuity because of the time span over which there's the inception of the concept of a space project and its conclusion and its full data analysis. So this is about a 20-year cycle. So in academia, you don't tend to have those kinds of very long time span cycles. I know this because I've worked very recently with a group of scientists, all very esteemed scientists who generally get their funds from National Science Foundation. And we worked on a project for a field project for Patagonia, in which we integrated seismology, a field called limnology for studying proglacial lakes, and also other environmental factors that surround the Patagonian ice fields. This was an 8-year project. This was huge and involved multiple millions of dollars. This is huge for National Science Foundation to fund something like this. Whereas when we have a satellite program, we're talking about $750 million for the project. And then there's, by the way, there's some peanuts involved for the scientists who analyze the data. But those peanuts turn out to be relatively large amounts of funding relative to what you'll get out of an individual National Science Foundation grant. So there are advantages in being in the National Science Foundation world, and that is that you can try to, with a good graduate student or postdoc, you can produce a lot of results in a relatively short period of time, but you tend to lack this continuity that you get by having a space program or a space project that's producing data over a time span of 2 decades, which has essentially been the case with our GRACE gravity program that has been so successful at JPL.
Erik, has your research always been tied to a major mission at JPL? Have you ever pursued something on a smaller scale just based on your own interests?
Well, actually, when I became involved in the geodynamics program at JPL, this was a program in which a lot of technology was going to be developed that would, in theory, help us understand plate tectonics and fault, how earthquakes are generated. And in the early stages of this, the technology was just barely kind of presenting itself in a way such that you could make any sense of it. So we had this period of time where we could pick out those areas where we thought geodesy was going to become successful, and the technology was going to become successful, and kind of use our knowledge of both models and of geological facts to be able to do research that was more focused on either smaller scale problems or problems that weren't necessarily tied to the current data set. And so that allowed me to be able to take some time to be able to understand California tectonics and the tectonics of the Western United States. So I found that to be very rewarding in the sense that I could really be looking at data sets that were generated by the U.S. Geological Survey, for example. And so, yeah, we do have periods of time in which we can kind of use our own scientific intuition to know where to look for smaller scale phenomenon that eventually will become something that NASA can use. Patagonia, for me, is a good example. We I had been working with colleagues on global problems of glacial isostatic adjustment and ongoing ice mass balance and how these affected solid Earth phenomenon and the gravity field. And I realized that turning back to smaller glacial systems, that if we had GPS receivers that were placed very close to these glacial systems that are currently in demise, that we might be able to see a vertical signal of the ongoing isostatic rebound as these systems had been deteriorating since about the turn of the century, 1900. So we should be able to be able to detect a vertical uplift. And so, in fact, we were able to determine a vertical uplift. But if I didn't have the opportunity within the science calls for the geodynamics program, I wouldn't have been able to spend the time to write the computer codes that then allow you to make that a justifiable prediction of this phenomenon. And then a field program can go out and measure it. And it is space technology that allows you to be able to do this. And in fact, we have a whole division at JPL that's telecommunications, and it's their driver to develop this kind of technology that has this capability. So we have engineers that are fully aware that we want to make these kinds of measurements.
Erik, over the course of your career at JPL, I'm curious if Caltech has been an asset for you. Have you had opportunity to collaborate with Caltech professors or interact with Caltech students?
Yeah, so I would say not so much with students, but we have had good collaborations periodically with Caltech professors. Now, I specifically say students because that may change in the future. And in fact, we even have an ongoing presidential fund in which we're actively working with the student. But historically, looking over the past 50 years, I would say generally the Caltech professor tends to be relatively protective of the graduate student, and only in very rare cases will the graduate student's influence be more from the NASA data set that's coming from JPL or another NASA facility. A good example of that would be a guy who currently is a senior scientist at JPL. I won't name who it is, but if you might have run into him at some time. Became involved in interpreting the lunar gravity field. And at the time, JPL was having a great difficulty finding people that were interested in doing a detailed understanding of the lunar gravity field. Well, this graduate student just sunk their teeth right into it, and it became the standard model for the gravity field of the moon. And I think the Caltech, I don't know who the Caltech professor was that was the advisor, but I think the advisor at Caltech just decided, well, the guy's so into it, just let him go. But that's a relatively rare case. And so usually we will write presidential funds with Caltech professors, and then if we wind up receiving a significant amount of the funds, we're really expected to do the research, or that has been my own personal history. And usually there have been good things that have come out of that.
Erik, I'm curious, having spent so long at JPL, if you've ever gotten involved or have lent your expertise to non-terrestrial science, looking at planetary science beyond Earth.
Oh yes, yeah. So when I was hired at JPL, I was hired using funds. When we're hired, we don't pay much attention to these things, but because we just figure the money is around. But in historical perspective, it's kind of interesting that I was hired to interpret lunar data from the Apollo program, and specifically related to the heat flow experiments. And so I became involved in building a computational capability to be able to do mantle convection for both Mars and the Moon. So I did gain a great deal of expertise about that, and particularly for Mars. So I'd always been kind of tempted to put my hat back into the ring of being an investigator for planetary science. But the problem for scientists um, within planetary science is that you had to become so involved in the long term project that it pretty much that that aspect of becoming involved in planetary science would suck up a great deal of your time. So there are some scientists at JPL who have worked in planetary science, and they've been pretty much able to completely fund themselves through the calls for science investigations. But the number of those scientists is very small. And so I offer an example of one who's very successful. Was my first office mate at JPL is Bruce Bannard,
Oh,
and
wow.
he is the PI of the InSight instrument.
Hmm.
And it's interesting, we also shared our PhD advisors, me much later than he. And I'm kind of interested in the topics that he worked on for his PhD thesis still today, and I can study those things within the context of terrestrial science and what's broadly called the geodynamics program of NASA. Bruce, in parallel, became involved in the development of the InSight instrument, the seismic instrument that was placed upon Mars. And it may not be appreciated by many people, but Bruce understood exactly how that instrument should be built, and in fact is responsible for the high quality of that instrument capability. So he had to make a decision. He was a very good, very well respected scientist within the Mars community in particular, and had done very nice modeling. But he had to make a decision as to whether he was going to dedicate himself to making sure that this planetary exploration endeavor, really great science, was going to be successful. And that absorbed most of his career. So you have to make a decision as to whether that's the kind of scientist you want to be, or you want to be a scientist that is constantly writing proposals that will keep you fully funded to do scientific research. And I decided the latter.
Erik, you have a tenure where you've seen so many directors of JPL come and go. Are there any directors that have been specifically impactful for your career that have emphasized the kind of research that you do?
Well, I'm a good friend of Mike Watkins's, so I would certainly say that I'm somewhat in parallel with Mike's research. Uh, but I wouldn't necessarily say so. And for all of the directors of JPL, I have a great deal of respect. Um, there isn't a director that of JPL in my entire career at JPL that I didn't like in one way or another. I remember when Lou Allen was brought to JPL, we were afraid that we were going to become a part of the sort of Ronald Reagan's Star Wars effort or something like that. And the Caltech faculty actually objected to the idea that JPL change its contract under which 90% of JPL's work is for NASA. And I think that was a turning point for JPL. And we credit the Caltech faculty for sticking up for the contract that is with Caltech and JPL and NASA. And Lou Allen was he was very much in line with that. Actually, he was a very good, as it turned out. He was from the Air Force, and it turned out that he was actually a very reasonable scientist. He had his own interests in balloon experiments at very high altitude for atmospheric science, actually. So I would say at every turn, I found that the qualities of the scientists that have become lab directors are very admirable.
Eric, you
I'd
mentioned.
also say, yeah, I'd also say that our characterizing science at JPL, we also have had good leadership in terms of our chief scientists. And those are very important people.
Eric, you mentioned NASA. Have you had opportunity for direct interface? Have there been cause for you to go to Washington and meet your peers at NASA?
Oh, yes, certainly. Yeah. So I've sat on review panels, and I've also been invited to some panels in which we met, for example, Soviet scientists at the very end of when the Cold War essentially became a thing of the past in 1990. Yeah, and there often are missions. There are programs in which our real partners are Goddard's Space Science, and so we have many meetings at Goddard Space Science. And we've come to know our colleagues at Goddard Space Science, very well. Sometimes we know some of our colleagues at Goddard better than we know our companions at JPL within the same science division.
Well, Eric, this has been great overview of your career. Let's go back and now establish some personal history. Let's start with your parents. Tell me a little bit about them.
Well, my parents, I guess, being a Southern Californian, maybe they are normal, maybe they're not so normal. My father's family history is they're Mormons, and my great grandfather was asked by the Mormon Church in the late 1890s to go to Mexico to become the leader or the leader of the stake, or however you refer to that, in one of the colonies that they had in Mexico. And these colonies were to avoid U.S. law against polygamy. And so they were polygamous colonies. My great grandfather was not a polygamist, and my grandfather did not grow up in a polygamist environment, or rather family, but he grew up in a polygamist environment. And it was also the time of the Mexican Revolution. And so my great grandfather actually, he not only met Pancho Villa, he was a friend of Pancho Villa. And so this kind of, when my grandfather's family moved back to the United States, to southern Utah, this history kind of characterized the way that my father, my grandfather, and of course my great grandfather viewed the world. And among all of the grandchildren of my great grandfather, my father most thoroughly aligned himself with this kind of worldview. And I mean, it was a worldview. It was not a regional, southern Utah view. And so he grew up on a dry farm in southern Utah, where you were really one with nature, and to the point at which he was much more comfortable riding a horse than he was cranking up a Model T. And he kept that attitude all of his life. And although he became kind of a man of the world, fought in the Second World War in North Africa and Sicily. He studied art in Geneva, Switzerland. He married a Norwegian. He always kept this very rural U.S. kind of cowboy approach to the world. Only he hated cowboys. So, I mean, that's kind of the background that my father had. He was very interested in science. I would say that his father was more of a scientist than he was. My grandfather actually taught animal husbandry, which is part of animal science, at Brigham Young University in the 1930s. And my grandfather was actually a missionary in Japan. And since he spoke Spanish and English very fluently, he was asked to translate the Book of Mormon into Japanese in Japan, in Tokyo, in about 19, I guess it was about 1911 to 1918 is when he was there. And he worked diligently at this, and he learned Japanese well enough to start reading texts that were associated with Shintoism. And he basically became a Shinto. So this is the big transition away from Mormonism that occurs in my family. So not only did my grandfather live in southern Utah and have three sons, but they all grew up kind of not believing in the Mormon religion because they believed in Shintoism, which is the belief in nature, which is the segue to growing up in northern Claremont around someone who totally believes in nature and understanding nature. And so that's a part of my history that actually goes way back to these experiences in southern Utah, and even going all the way back to the colonies in Mexico. Now, my mother also can be credited for science and my science education because she grew up during her father was a sea captain in Stavanger, Norway. And to become a sea captain, you basically have to be the kid in the class that scores the highest on your math tests. And then they send you off to do navigation and become a sea captain. That's the tradition in at that particular time, the turn of the century in Norway. And so he became the captain of a ship, and he was gone at sea for most of the time. And the household was basically run by women. The mother and my mother, who was and my aunt, and they had an appreciation for science. Mathematics in particular. They always believed that you should study mathematics as well as you can. And the Germans took over Stavanger in September of 1939, and relations, you might say, were rather hostile between the Germans and the Norwegians, although the Germans will never tell you that. My grandfather's ship was taken over, and he was basically lost his ship. It became part of the Third Reich's military operations. And so the family decided that they would leave Stavanger and go back to the traditional fjordlands where their traditional family had lived, where they didn't really run into the Nazis very much. They were kind of escapes from them. And so my mother grew up in a very rural, as a teenager, grew up in a very rural environment in which, they were using boats in the fjords. And so she had been someone who was very close to nature. And so not only very close to nature, but believed in a strong science education. So when I grew up in Southern California, she would always introduce me to some science program that was for elementary school kids. And I would always, wind up in that. So So while other kids were going off and playing baseball or playing tennis or something like that, I was going off to a little science camp. So that was very influential.
And where
So
did
my parents actually are very unique in the sense that they were very close to nature in very, very intimate, strong ways.
and you mentioned Claremont, is that where you grew up?
Yes, right.
And was
Mhm.
was that more suburban, more rural when you were a kid?
Very rural. We lived north of Baseline Avenue, which during that time was all orange groves or chaparral. And so we were on a piece of property that was surrounded on several sides by orange groves, but to the south of us was all chaparral. So we were always out with, the snakes and the lizards and the rabbits and the chaparral environment.
When did that area really start to get built up? Was it during your
Oh,
childhood?
yeah, during my childhood, because in about 1960 is when the rumors of land developers who wanted to build houses started to come to those who owned the orange groves. So I knew some of my friends whose fathers owned orange groves. They were actually lemon groves. Started to get proposals from people who wanted to buy their land for development. So it very rapid between 1960 and 1967, which is when I went off to college. Suddenly, we had these housing developments that had grown up within the orange groves, and so suburbia had come.
When it was time to think about college, were you already focused on science? Was that the career track you wanted to pursue?
Not necessarily. I was more passionate about history and even economics and psychology. And so I had a potpourri of things that I was interested in pursuing. But one of the things that maybe it was partly my personality. I'm rather a shy person. So when it comes to delving in psychology and it tends to invite people that are good at verbalizing themselves. And what I found in both biology and physics was that um, you relied upon the ability to understand um, uh, quantitative relationships, let's say. And I found that to be internally quite satisfying. And I'd always been in high school. I'd always been good at physics, so physics was a natural avenue to follow.
Was the draft something you needed to deal with? Was the prospect of going to Vietnam a reality for you?
Oh yeah, yeah, it was. Yes, yeah. So being in school was a good thing, and they developed this numbering system. I think it was when Nixon was president. So they drew lots for a numbering system based upon your birthday, and I got a number that was like 307. So I was I was basically not going to be drafted when I finished college, which was a great benefit. I had roommates who all got low numbers, and they all had to do all kinds of various things to escape the draft. And I had one roommate who was probably the best physics student we had at Cal Poly. He had to escape. He had to leave the country. He went to Canada. He was not a U.S. citizen either. He was a citizen of Argentina.
Eric, tell me about your
He was the
experiences
president.
at Cal Polytechnic Pomona.
Uh, Good education is what I would say. Since I went off to graduate school at UCLA, UCLA was hyper focused on research and not so much at teaching. Whereas at Cal Poly, I mean, you got very good teachers, especially in physics. And I think the time was very unique for that because we had one professor who went on to write a great undergraduate physics textbook named Douglas Giancoli. He went later to UC Berkeley, and started a physics education program there. And he was a high energy physicist who basically burned out on high energy physics research. But he knew all of the he knew all of modern physics. And when we took his courses, it was like he was like Aristotle, to us. And he was just fantastic. You know, I probably wouldn't have a career where I could have applied to UCLA if it wasn't for him.
Being a college student in the late 60s and early 70s, was the counterculture relevant on campus at all? Did you see any of that?
Oh, of course. I mean, even at an engineering and agricultural school like Cal Poly, it was definitely there. And the circumstances. I remember in my freshman year, we had the assassination of Martin Luther King, followed by the assassination of Robert Kennedy. Was These were tumultuous times, and the Black student movement and the Chicano movement were all getting going really strong. So yeah, these were tumultuous times. So I mean, when you think about it, I mean, I had all of these interests, history and so on. To be able to kind of settle on physics was one way of seeing the world in a less chaotic state. In fact, much later in my career, when chaos theory became a little bit in vogue, there was somebody who was a secretary who once asked me, "Oh, Erik, aren't you going to take the courses in chaos theory?" And I said, "Look, my research is all about stability theory, no chaos theory."
Erik, as an undergraduate, did you have exposure to geophysics or earth science at all?
As an undergraduate, no, not really, not in any meaningful way. I took a geology course, which was called historical geology, where all we were supposed to do is figure out what a sedimentary history was based upon faulting and reorganization. So it just wasn't meaningful at all. I mean, the most meaningful thing that I took as an undergraduate that was applied uh, to geophysics was mathematical was in the math department, studying Legendre polynomials and Bessel functions, and then differential equations, and then high pressure statistical mechanics and thermodynamics, and those became essential to studying geophysics.
And so then, without so much of a background, how did that lead you to the geophysics program at UCLA?
Oh, I wouldn't say that. I would say at the geophysics program at UCLA, at that time didn't require any understanding whatsoever of geology. In fact, the way the department was run, if you were a geologist, there was no way you were gonna make it very far. You had to be a physicist. In fact, we were required to take physics courses in the physics department.
Now, did you start at UCLA directly after college, or did you work in
Yes,
between?
yes, I did. I went directly to UCLA. So I entered as a 21-year-old.
And was this a terminal master's program, or could you have stayed on for the PhD?
I could have stayed on for the PhD, but I started working at JPL, and JPL was so fascinating to work at. And I think at one time I was told, what the research that you're doing with Roger Phillips is in direct uh, opposition to some of the research that's being done by UCLA professors. So you better watch out.
So, what was that initial opportunity? What was the point of contact that got you to JPL?
Oh, actually, it was one of the guys that was in one of the classes, the battery of courses that we were told to take in the first year of graduate school, was a JPL radar scientist. He also happened to be had a lot of money to do planetary radar sciences, and so he hired. I think he hired three of us, and so we all got to go out there and interview at JPL. And so I think that during the interview process, they said, you really ought to go and talk to this guy, Roger Phillips, because he really does mantle stuff, and you're more interested in mantle stuff. And so I went down and I talked to Roger Phillips, and that's how I got a job. So it was really this individual at JPL who didn't have a PhD but wanted to go back and get a PhD, who kind of instilled this excitement in many of us about research at JPL. And one of the people that he also hired was Charles Alachi. So in those very early years, at lunch, we were with not only Walt Brown, who was the person who had hired us, but Charles Alachi, who later became the director at JPL.
Erik, when you accepted that offer to join JPL, did you have at the back of your mind that one day you'd return to graduate school to finish the PhD?
Yeah, yeah, yeah,
Tell me
yeah,
about your
certainly.
initial work at JPL. What were you involved in from day one?
Well, there had been a proposal that had been written by someone at JPL who was quite a gifted scientist, and I would say he was from the old school of analytical approaches to geophysics problems. His advisor was actually Barclay Cam at Caltech. And Barclay had very similar kind of a guy. He was extraordinarily good at both observations and analytical theory. And this particular individual's proposal had been rejected by the NASA panel, and he was very upset about this fact. And the reason that this proposal had been rejected was because it did not have the fluid transport of heat owing to mantle convection. So I was given the prospect of writing mantle convection code, and so that was my first project at JPL.
And where did you sit administratively? What division or section was it?
There was a reorganization that had occurred. There was a science division, but the sections had been reorganized, and we were called the planetary science section. So while there wasn't a planetary science section when I was hired, that was the section that we became. So we became the planetary sciences section. It did remote sensing, and it did Earth gravity fields and geophysics.
What were the major missions happening at JPL in the early and mid 70s that were important for you?
Well, there was Viking, and there was Viking 1 and there was Viking 2. After that, there wasn't much because we had such a flurry of data, the Mercury missions, uh, such that most of what we were relying on was data analysis. So it was lunar data analysis and Martian data analysis. And there was a prospect of a mission to Venus. But actually, what had happened, NASA had gotten so much money during the 60s to basically compete to get to the moon and Mars, that there was a dry spell that occurred when Bruce Murray became the manager or the director at JPL. And in fact, what we called it the purple pigeon era of JPL. And this was an era in which JPL was struggling to find a new flagship sort of mission that could be the focus of a lot of engineering activity at JPL. So there was a fear that JPL had kind of lost its direction in terms of having a new post Viking era a mission. And of course, the mission that did replace it, the flagship mission, was the Voyager mission. And so there was a tremendous amount of effort between, well, say, 1978 and 1982 to get this Voyager mission basically off the ground, going from just table talk around the table to actually agreeing on being able to cut metal and start the project.
Did you
That was
ever
a very difficult era of JPL.
did you ever interact with Ed Stone? Did you see him in action during these early years?
No, I did not, because I was not. I had made this decision in 1982 to go into geodynamics because I saw terrestrial science as being a place where not only did my understanding of mantle convection lend itself to the current data sets that were being produced, and those data sets involved seismology. We learned when the IRIS global seismological system was put together in, I think, about 1975 to 1977. The data sets that were produced dramatically changed our understanding of the Earth. I'll give you an example of how dramatically they changed our understanding of the Earth. Is that in 1981, Adam Zalonsky and Don Anderson at Caltech produced a paper called Preliminary Earth Model, and it was called, later became known as PREM. And that preliminary Earth model is so preliminary that we're still using it. That's how profound the seismological community had changed how we understand the Earth. Now, it was put me in a kind of a situation where we have geodesy coming, and we have this profound new understanding of the interior of the Earth. And how do we put these two things together? And there were a small number of geodetic scientists who understood the importance of this. And I have to say, without the existence of those people, I would have been a lone island. But John Moore is one scientist who particularly stands out in the memory of the 1980s, who had produced a PhD thesis at the University of Colorado that just profoundly changed our understanding of Earth tides. And Earth tides are, of course, related to the elasticity that comes out of this preliminary Earth model. So Earth science had suddenly exploded right in this period where we were struggling to get new space data for scientists from new projects. And so I recognized this opportunity to work in Earth science, and in particular to work on this on mantle geophysics, which had greatly expanded its capabilities by having this global seismic network.
Erik, you alluded to it, but it bears going into a little more detail. In the early 1980s, when you made this switch, what were some of the key technologies that made this field exciting and compelling for you?
Oh, well, one of them was VLBI, very long baseline interferometry. And the idea of very long baseline interferometry is that you understand quasars very, very well. And so these antennas are huge. They're the size of many basketball courts put together in radius. And these are capable of being able to determine not only to kind of detect quasars, but they're able to understand the waves that are emanated by quasars very well. And they are used to study astrophysics. And it turns out that because of some scientists that worked at the astrophysical lab at MIT, Erwin Shapiro in particular, the concept of being able to use these to study plate tectonics was put forward in the mid 1970s. And a lot of people were very skeptical that this would be feasible, partly because they didn't quite understand what the noise level would be around a VLBI facility. Goldstone is an example. The Goldstone antennas are an example of what a VLBI center could be. But the capability was such that one could understand the phase of the signals that were coming out of the quasars very, very well. And so he locked onto the same phase with a global system of VLBI antennas and understood how this phase, the locking, shifted over time. You could make a time series that would tell you where the plates were going. And so this actually turned out to work, which surprised a large part of the community. A large part of the community thought this is a theoretical idea. People don't understand what the full noise systems are, but it actually over the course of about a decade, it was shown to actually work.
Erik, in the early
And
1980s, what aspects of plate tectonics felt like settled science, and what were some of the big debates at that point?
well, I think one of the things that those of us who were required to understand have an in-depth understanding of the science that went into the possibility of doing space measurements, which VLBI was one, was what do we already know? And what we already knew about plate tectonics was largely known because we know how to map the magnetic variations of the Earth's core in newly formed basalts that form at mid-ocean ridges. And so by also understanding the geometry of earthquakes that are associated with both the region where ocean spreading is occurring and subduction zones, we get a very good idea of both the rate at which plates are moving, the direction in which plates are moving, and therefore can put together a system by which basically the geometry, and it was actually research that was done at Caltech by Dan McKenzie that was one of the forerunning papers on this in the 1960s. So those of us who were well aware of this type of science we already knew pretty much where the plates were going. And so the question was, how much better could we do if we had these space measurements? And it turns out we could do a lot better because we know this data from the ocean floors, which is 67% of the planet. So we have a very good idea where the plates are moving, and actually a lot about how the plate system works because we have heat flow experiments that tell us how the heat flow drops off away from the mid-ocean ridges and the topography. But we didn't have a quantitative sense for how to use that space data to be able to do a little bit better. And it turns out by doing a little bit better, we understand continental tectonics a lot better. So the focus during the late 1980s was to try to be able to develop a system by which we could understand the Western United States and its tectonics. I mean, naturally, tectonics is occurring everywhere, but since we NASA live in the United States, targeting the Western United States was a very opportune thing for the geodynamics program to focus on. And that turned out to be successful because GPS became successful as a geodetic technique.
Erik, tell me about some of your work in thermal convection during this time.
Yeah, so at that time, the codes that were being written were almost exclusively finite element programs. So, for example, there would be classical finite element programs that could be written for spheres, because in mechanical engineering, you look at the deformation of the interior of spheres. You can also do fluid dynamics for the interior of spheres. But one of the things that characterizes the kind of convection that we want to simulate for a planetary interior is that the differential equations that govern the free thermal convection are nonlinear and they're higher order. They're sixth order partial differential equations. So they're rather challenging mathematically. The technique that I developed was a spectral technique, and we took on the problem of temperature-dependent viscosity, which makes the equations even much more nonlinear. And so that was a major effort to try to develop a new computer program that would do the simulation of a temperature-dependent viscosity planetary heat transport. And what I did was I tried to develop enough simulations so that we could get a scaling law between the amplitude, an amplitude measure of the interior convective rate to the heat transport that would come out of the planet. And so this goes back to the original Apollo funding, where this proposal had been rejected because we don't have this fluid transport. So I successfully developed a program that would do that, and that became part of one of the first publications that I did at JPL.
And was this associated with, or did it rely on data from a specific JPL mission?
No, no, except that we were asked to match the plate motions, the lack of plate motions on Mars, and also the heat flow data on the moon. However, what I found in working with the fluid dynamical equations was that it was much more important to try to get these scaling relationships, because if you had the scaling relationships, then you could apply it to Mercury and Venus, and you could apply it to all of the icy satellites. So that was my focus, basically, was basically a more general approach to being able to use the computer program to be able to generate generalizations that could be applied to all of the terrestrial planets.
Moving into the mid-1980s, just a nomenclature question. Interplate shear zone, what does that mean?
Interplate shear zone. Well, what had happened by I would say the mid to late 1970s was the U.S. Geological Survey had done enough geodetic experiments so that they understood that the interaction between the North American plate and the Pacific plate was spread out over a zone. And they didn't know, it was debatable how far this zone was. Was it from the Sierra Nevadas to someplace, some offshore fault to the wall? Enough earthquake data. We didn't understand enough about earthquake mechanics to be able to extrapolate from the fact that there was an earthquake to what it meant about regional tectonics. So the question was, we knew the shear zone existed. We just didn't know. We didn't know the details. We didn't know how wide it was, and we didn't know how intense it was. And we didn't know its temporal structure either. In fact, we're still dealing with that.
Erik, when did you start to get involved with cryospheric research?
Well, I started getting involved in cryospheric research when through this paper that was published it actually appeared in the literature in 1985, I believe, by Mark Meyer. And this is global. This relates to another space program that JPL had in collaboration with University of Texas and Goddard, and also with the French. And there was two spacecraft that were at very high orbit. One was at 1 Earth radii, and the other one was at about half an Earth radii. These are up high enough so that they can be in very drag-free environments. So they were spheres. And there was a laser system. Originally, it was proposed that this laser system could help us understand plate tectonics. So we would have a freely orbiting object in space that entirely was driven by the Earth's gravity field. So its orbit, we could determine its orbit extremely accurately by placing a set of mirrors on the sphere. It was about the size of a basketball. and determine its orbit so well that we could understand how the Earth's gravity field was changing in terms of both the position and in terms of the long-term nature of the gravity field would drift uh, because of climate, because of not only climate change but also because of post-glacial rebound. So this concept of being able to measure time-dependent gravity from these types of observations was actually suggested by a Japanese scientist in the early 1960s. And this idea had actually been around amongst people that knew satellite geodesy fairly well. And so they launched these space, since it was rather simple. You have a sphere, you launch it into space, then you do laser tracking of it. And so this was a project that actually gotten started in 1976. So we already had a lot of data. So this is how we made the link to sea level rise and glacier mass. So it actually turned out to be a sphere that was this big around
I
with
got to
mirrors on it.
I got to know Charlie Samus during my time documenting the history of the Seismo Lab. What was some of your collaborations with Charlie? How did you get to know him?
I got to know Charlie Samus through Bruce Banner. Yeah, so I knew what Charlie did, and I realized that there was an alignment between what Charlie did and what his interests were. In fact, basically, rheological sciences is one of his passions, and understanding rheological sciences from a kind of just not just an engineering background, but also from kind of a very artistic. Yeah, he has a very artistic way of thinking about these things. So I found interaction with Charlie to be really fun.
And that gets me to my next question. How does rheology work on a planetary scale? I understand rheology, in a laboratory environment, but how do we look
Mhm.
at plate tectonics, geodynamics from a rheological perspective? How does that work?
So I might point you to the most extreme example, and that would be the planet Io. And Io, basically, what I call Io is I call it the ball bearing, the hot ball bearing of the Jovian satellite system, because it's the place where all of the tidal dissipation is kind of forced into this one area, and so it winds up with a very high temperature, and so it winds up with a system that's constantly belching out these plumes of material because it basically has these water ice volcanoes in it. So it naturally has to have a planetary environment that is very fluid. And so the question becomes then, well, how fluid is fluid? Are you talking about fluid such that are you talking about fluid that would be like the material like you'd find in a cold jar of honey in your refrigerator? Or is it comparable to anything we find in solid Earth material on Earth? And the fact is for Io to operate the way Io does in its interior, it has to be much lower in viscosity. I would say I'd say one of the questions then becomes, if you look at another example, which would be, say, Venus, what's the viscosity of the interior of Venus? Well, we don't know the answer to this question within many orders of magnitude. So it becomes a question of what clever things can we come up with that will tell us what this time scale is. So in trying to understand rheology on a planetary scale, always comes down to how can we measure what change that occurs over a period of time? Because this is basically what viscosity is it's a coefficient that stands between the rate of deformation and stress. And so if we know something about stress and we know something about the rate of deformation, then we can infer something about the viscosity. So if we're looking at a planet like Venus, then we've got to make this connection between timescale and stress, and we've got to know something about stress. we got to make some kind of observation about the rate of deformation. And so that's one of the key things that we want to get at in future planetary science studies to be able to make better inferences of what the viscosity is.
Eric, as you were explaining earlier in our conversation, the rate of sea level rise right now is beyond anything that we've seen in geological history. When you started to think
Well,
about these,
not in geological history, but within the last 5,000 years.
yeah, right, okay, good. Thank you for clarifying. So
Yeah.
when you started to think about these things in the 1990s and you were thinking about sea level rise and its relationship to Earth deformation and gravity and cryospheric research, was it then that it became obvious that the human caused aspects of sea level change really separated it from these other natural processes?
Oh, that's a very difficult question because we have had this phenomenon called the Little Ice Age that occurred sometime between 1500 and 1900, and depending upon which region you're in, this can be very variable. But we believe that in North America and Europe, that the Little Ice Age occurred sometime around its maximum occurred sometime around 1870, and so we emerged out of the Little Ice Age. And the question is, how much of an impact does that little emerging out of that Little Ice Age? Where does it intersect with what are human caused sea level rise? And so one of the things that we can understand is that the Little Ice Age is a phenomenon that even if it's the largest, what are called neoglacial events, global neoglacial events that occur during this 5,000 year period, this what's called the late Holocene in cryospheric and quaternary sciences. We are quite sure that we never had any kind of emergence out of one of these neoglacial periods that is as ferocious as what we now have. But finding that kind of sweet spot that defines the difference between anthropogenic induced changes and how we're evolving out of the end of the little ice age, which is terminated at about 1870, is a difficult question. Is a question of ongoing research. I currently have a paper in review where I try to couch the ongoing uplift that we see, very rapid uplift that we see around glacial systems in the solid Earth, and connect that to what we see from post-seismic events. And I realized that we have to sort of move our paradigm to a new kind of theoretical expressions for how we define rheology in these simulations. And I kind of like to think that 1945 is the time at which we can start to quantify what our impacts are on the environment, because the post-war industrialization occurs at such a rapid rate, and that there's a defining horizon within the geological horizon. It's called the bomb horizon, and that's when the first nuclear tests were done. They put out so many, strontium 90, and they put out so many short-lived radioactives that it's very easy to define. In fact, what it does is it kind of messes up radiocarbon dating. So people that do radiocarbon dating are very familiar with this particular horizon, and you can find it globally. You find it in the ice cores. So that's what I define as kind of the beginning of the Anthropocene. People have different definitions, but that's kind of a nice one that you can. There's both a rationale for it because of this post-industrialization and post-war industrialization and this horizon.
Eric, tell me about your decision to return to graduate school at USC to complete your PhD.
Oh well, there was a friend of mine who very close friend at JPL who's Slovakian, and he he was in the radar. He was in radar sciences, and he was actually on the Cassini. He was one of the Cassini radar scientists, basically Charles's right hand man on the Cassini radar mission and radar experiments. And he sat me down sometime in the late 1980s, and he says, "Eric, with all the research that you're doing, you're going to be a research scientist for the rest of your life. So you just don't have the union card. And here's a guy whose his father was taken off to Auschwitz. He had to watch the Soviets come in on literally seeing the tanks come on the battlefield when he was a young man. So I knew this person. He had escaped, the Iron Curtain in the 1960s out of Czechoslovakia. So I knew this was a person who really understood the world. He sat me down. He says, "Eric, this is just he and I at lunch one day." He says, "You have to get a PhD, because if you don't get a PhD, you're going to find yourself just kind of like without a union card, and you're going to be in your neck. You're going to be too old to be competing with people who have the PhD, who are young new scientists." And I took him at his word. We have a few people that do not have PhDs in my field. Some of them are quite famous, but I didn't see the trajectory of my career going in that very fortunate path.
Given all of your experience, was the PhD somewhat fast-tracked for you?
Yeah, I'd say I enjoyed it so much that I probably took more time than I should have, but it was what it was.
Now, did you take a leave from JPL, or you did it part-time?
No, JPL, there was a program in which if your section approved, they would pay your tuition. So JPL paid my tuition. I was still required to write proposals at JPL as principal investigator. So this was kind of a dual thing. I had to both be a student and be a competitive research scientist at JPL. So it was a lot of work.
Was the thesis directly responsive to what you were doing at JPL?
Yes, yes, it certainly was. Yes. So the PhD thesis at the time, we had beautiful geodetic observations of the post-seismic mantle flow that was occurring after the Landers earthquake in 1994. And this was a big topic not only at the Southern California Earthquake Center, but also within NASA as well. And one of the things that they had to understand was, why was everything flowing so rapidly and over such a large area and for so long? And so the rheological model that Charlie and I conceptualized and put together and quantified was something that could explain this. In fact, it did explain the timescales.
By the mid-1990s, was your sense that JPL was fully invested in earth science generally and climate change research specifically?
No, I did not. I did not believe that. And in fact, I think one of the, I became a little bit more closely in tune with what the ocean sciences group was doing at JPL. And they also had this sense that climate change was not really something that we were supposed to talk about. It was because we had Al Gore, who was a great proponent of studying climate change, but it wasn't clear that NASA wanted to take the step of saying, we are going to involve ourselves in the study of climate change, because it was more of a question of quantifying things like the rise of carbon in the atmosphere. This is an observation. This is not the study of climate science. So I did not feel as though NASA necessarily embraced the idea of studying climate change. However, we in ocean sciences, we had this rise of sea level that was being observed, by the late 1990s, since the project began in about 1992. We also had remote sensing observations of the cryosphere, which demonstrated the rapid nature of changes that were occurring in the cryosphere. So you go to a cryosphere meeting, and everyone would be talking about the disappearance of mountain glaciers. However, what was known about the ice sheets was still in great debate. Some NASA scientists favored growth of the ice sheets, and some scientists favored their shrinkage. But the numbers were all very small. We didn't think that ice sheets were really contributing to sea level rise very much. That all changed in the 2000s.
So to return to this earlier point, it seems, in retrospect, the connections would be obvious between cryospheric change and sea level rise, but where does Earth deformation and gravity play a role here?
Oh, well, it plays a role in corrupting the data signal that we obtain from the gravity signal. So in other words, if we have a spacecraft that's only measuring the gravity change on the Earth, we have two signals that we have to worry about. We have to worry about, we have more signals than that, but two competing signals are the fact that the surface mass is changing and shifting and moving around. It's not disappearing, but it's taking mass that's on continents and moving it into the oceans. We also have places that are very interesting, like the Amazon, where not only do you have huge seasonal changes, but you also have decadal scale changes. So when these phenomena occur, you have the solid Earth, which encompasses a very long wavelength gravity field of the Earth that's also changing simultaneously, in part in response to the changes in the surface load, which causes change in stress and therefore cause creep in the mantle. But we also have this longer term phenomenon that comes from the last glacial age. And I think you mentioned earlier that we didn't have that in the geological record, we don't necessarily have rapid sea level changes, but actually at about 18,000 years ago and about 14,000 years ago and about, again, at 12,000 years ago, we have huge changes that occur in the system. And these cause deep responses deep in the mantle, hundreds of kilometers down, thousands of kilometers down, even change in the shape of the core mantle boundary that also cause changes in the gravity field. Those have to be filtered out, and they're one of the more difficult things to filter out. So this fact of this corruption of this very important gravity signature that is related to water changes on the surface of the Earth has to be modeled and removed. And so this is something that is absolutely required to run a gravity mission that will get you detailed information about how the ice sheets are changing.
Eric, you mentioned this debate, this scientific disagreement about ice sheet loss versus growth. Your work in the late 1990s in Patagonia, was your focus on land uplift and you took it as face value that the glacial would shrink, or were you actually part of that argument that we would see glacier shrinkage?
No, actually, there was historical data that was remote sensing data that occurred right after 1945. And this was because in war times, it was called the Army Air Force. The Air Force was part of the Army. My father was a pilot in the Second World War, but he was always part of the Army Air Force. They took a special camera and they went throughout the Andes and they photographed the entire mountain range system with these photographs that had three cameras that basically allowed you to be able to do geometrical rectification so that you knew the geometry of what you were looking at. And they did this these were classified defense photography that was designed for any future conflict that we might have with any country, Asia or Russia or whatever. And these were picked up by glaciological scientists, many of them who were working in Japan. So the Japanese actually got a hold of these and they interpreted them over the years, because then they were able to go back and they were able to establish a baseline for what the geometry of the glaciers were. And then they were able to compare them to photography that was taken later in the 1950s. And they were able to actually develop a kind of crude time series so they knew the glaciers were shrinking. So starting in the 1990s, there were altimetry measurements that were made over the Patagonian ice system. So we already had some knowledge that we could quantify how the glaciers were changing. So it became a kind of a good kind of isolated, because we didn't have to worry about unmeasured areas. So to be able to conduct kind of a study of what this shrinkage might do to the mantle. So it was a place where we already knew the glaciers were shrinking. We had quantitative estimates of what those rates were. So it was a perfect little laboratory, terrestrial laboratory, to study mantle geophysics.
Erik, you mentioned it was only in the 2000s that the scientific establishment coalesced around ice shrinkage. What were the developments that led to that?
Well, it actually kind of goes back. You have to understand how crude things were in the 1980s. So although our ability to be able to do technology in the 1980s was quite significant, the vastness of the Antarctic interior meant that glaciologists had to go out with stakes. They actually put stakes in the ground, came back a year later and saw how much snow accumulated. Well, they were putting these stakes all in very coastal regions. And so naturally, they were seeing a lot of accumulation because this is where all the precipitation occurs. But they had no ability to be able to understand what the flow characteristics of all of the outlet glaciers were, because you just had to make too many measurements. So the bias was that the ice sheets are stable because there's so much accumulation that's occurring. And all estimates were that, and these were really quite good scientists that were making these estimations, that the ice sheets generally are growing at current time. And it was because of the bias that was created by the fact that you didn't have space observations that could allow quantification. Sometime in the 1980s, and I believe Barclay Cam was involved in this, we began to understand that using remote sensing, we could understand what the Antarctic ice sheet was doing in terms of its flow systems, where they were. But we didn't have a measure of how quickly the ice was moving out of Antarctica. So using radar interferometry, it was Erik Ivins that was the first one that determined that we could determine the change in the grounding line and also in the ice velocity at the terminus of outlet glaciers. So we got a new sense for how we could quantify the outflux. So along comes radar altimetry, which starts to occur in the early 1990s. And this radar altimetry also gives us a sense for how the height changes. And the problem is that the signal is corrupted by the various calibrations that have to be done. So there was a lot of controversy as to how to interpret this radar signal that was coming from both Greenland and Antarctica in terms of the height changes. And so there was a raging debate that was occurring within about 1998 to about 2002 over this: are the ice sheets gaining mass, or are they shrinking in mass? Well, the thing that kind of became crucial was that we developed ways to be able to measure the outflux velocity using remote sensing very accurately. We also developed a computational capability to use atmospheric data and reanalyze that atmospheric data and make very good models of the amount of snow that was falling on Greenland and Antarctica to within plus minus 5%. And so knowing the outflux and knowing the influx meant we were able to build models of what the rate at which the changes in these processes were occurring. And they suggested negative mass balance. Along comes gravity, and we have an overwhelming signal that tells us Greenland is losing mass. Overwhelming signal. So gravity is really it's kind of like you've got a golf ball on the green and you just want one putt to put the ball in the hole. And it's a long putt. Well, that long putt wound up being space gravity.
Erik, many questions on the GRACE mission, but first some background. What were the prior missions upon which GRACE was built? How did it advance previous missions?
Yeah, so yeah, I would say the whole NASA gravity program, including the lunar gravity program, contributed to this. Um, Gravity, let me give you some historical context. When I was a child, the big event that occurred in space sciences was Sputnik. And Sputnik was a kind of a joke satellite in some ways. It was just a technological demonstration that the Soviet Union could put something into orbit, have it come around, and they would know where it is. Actually, they didn't know where it is. The US knew where it was because the US did the tracking of the Sputnik space satellite because we had much better tracking technology. So one of the things that came about the tracking of the Sputnik satellite was we determined that the Earth had a pear shape. And the pear shape was caused by the gravity field that affected the Sputnik satellite. And so what this pear shape is basically the first order determination of satellite geodesy. And so determining orbits is intimately connected to how you measure the Earth's gravity field. And that's how this concept of putting these balls way up in space, these basketball-sized objects, and putting reflectors on them occurs. And at the time, one of the problems is to try to be able to determine not only the time dependence of the change in the oblateness of the Earth, which is basically the potato shape of the Earth, as opposed to the pear shape. And we had a great deal of difficulty in being able to determine the time rate of change of the pear shape of the Earth, which would have been very important for understanding the mass balance of Antarctica. So we already knew from this space mission that we had that was basically initiated in 1976, and for which we had data that was going all the way into the 1990s. How are we going to be able to determine the lower order time dependence of the Earth's gravity field that would therefore be related to the mass balance of the ice sheets? And there had been another program that had been thought about by space scientists that did space gravity earlier on, and that is to put a pair of satellites that would track one another. And as they flew over a region that had more mass, the trailing satellite would accelerate towards the mass, and even the lead satellite would be attracted back to the mass. And so you'd have this, if you arranged between the two satellites, you could tell where mass was and where a mass or a mass deficiency was. And if you had these two satellites tracking one another for years and years and years, then you would be able to determine what the rate of change of the mass is below. And that people understood that this technology could be investigated. The problem was is that we didn't know enough about how to accurately track these two satellites. And as the technology developed so that we understood both using GPS and understanding the onboard satellite technology and all aspects, thermal and all kinds of control that we have on what's affecting the distance between these two satellites, then we were able to get the GRACE program off the mat. But the concept had been around maybe for 20 years before that.
Now, were you involved from the beginning on conceptualizing and launching the GRACE program?
No, no. I would say that the champion of that was Byron Tapley and Mike Watkins. I mean, because we didn't understand what kind of breakthroughs there could be in that technology. So it was really Mike and a lot of very good engineers at JPL that spearheaded that. So we began to understand. I personally began to understand how that was going to come help to fruition by about the year 2000. And so I was completely on board with the mission concepts and the mapping capabilities. And in fact, I remember running into Mike in the cafeteria shortly before it was going to be launched, and I said, "Do you really?" I said, "Do you really think we can get so accurate to be able to measure Greenland ice mass balance?" And he said, "Well, maybe not." And it's one of these things. This is one of the surprising things I think in all of space exploration is that you actually get there, you actually get the data, and it turns out the data is just overwhelming. It's just it's one of the fun things about space sciences.
Eric, you've alluded to it, but
this stunning data.
You've alluded to it, but just to go into a little more detail, what were the primary scientific objectives of GRACE, and what were the engineering breakthroughs required to get there?
Yeah, so the big driver of GRACE turns out not to be a scientific objective. I mean, this is really weird because GRACE, there was so much skepticism over the success of GRACE is that it was flown as an experimental mission, meaning that we are going to see how well you guys can do your technology. And we expect that there's going to be a 3-year mission, and we expect that we might be able to find water changes that might occur across the entire United States over that 3-year period, or the Amazon. The Amazon was one of the big targets. It was one of the big advertisements. We can determine the gravity changes of the Amazon basin. And it turned out we could do a lot more.
When launch day happened, what were your interests? What were your hopes? What did you hope that it would accomplish?
Well, since it was launched in northern Russia, I was hoping it just got up there and went through the first phases of its calibration. And the data wasn't released very quickly because there's a lot of post-processing that occurs at a very basic level with the GRACE program. And University of Texas and JPL, they had extraordinarily competent engineers that worked on this data this part of the data analysis to take the distance between these two spacecraft and make good science out of it. And they did, and that took about a year from the time that it was launched to the time that it was released. And I knew what was coming down the pipeline, so I was all ready. As soon as the first data were releases, I was ready to make gravity maps. And I think people were a little bit surprised because I wasn't on the GRACE science team that had been doing a lot of the pre-estimates of these things. So suddenly the people at the University of Texas were saying, "Who is this guy, Ivins?" And so, one of the things about the Grace science team is that they're extraordinarily happy to have users. This isn't necessarily the case in planetary science, where the discovery, so much investment has been made by the scientists that have been promoting and overseeing engineering, that they're not so happy to be sharing the data as soon as it becomes available. Whereas in the Grace science team, this was quite the opposite was the case.
Now, the collaboration with Texas, did that run through Mike Watkins? Was he the connecting point there?
Well, what had happened in the 1970s is that Byron Tapley taught courses on satellite gravity. There were not very many competitors. And so he had a staff of people at Center for Space Research that had intimate knowledge of orbital mechanics and the data reduction processes. So yeah, he basically had built a graduate school that had a large number of people that were very good at understanding the software and the engineering. And Mike was certainly one of those people. He came out of that group.
When the data started to come in, what was it telling you? What were some of the new things we could know?
Well, when the first data that we got was basically to build a gravity map of the Earth. And we had never had gravity fields for the Arctic Ocean. And we had never had gravity fields for Antarctica. So since I had expertise in understanding Antarctica, understanding its morphology and its basins, basically where the ice was and where the rock was, I first looked at the gravity field over Antarctica, and you could immediately see the basins. You could see the geological structure just immediately. And I actually reported this, I think, at the first meeting in Germany where Grace data had become available. And we were not supposed to talk about Grace. We were supposed to talk about a German gravity mission. But I used both the German data and the new Grace data. And I remember the heads of the German aspect of the Grace project and Byron Tapley, the head of the American effort. They had shock and horror when suddenly I showed a Grace map of Antarctica that I had been able to reduce from the spherical harmonic coefficients. But it was all just beautiful. You could see all of the Wilkes Basin in East Antarctica. You could see all of this geological structure. And so I said, hey, you guys, you have science. You've already done science right here. Nobody's seen this gravity field before.
Erik,
so they were quite pleased by that.
What was the critical mass of data and even some of the theoretical advances where in the early 2010s it became obvious that you could make some pretty definite conclusions about ice sheet and glacial mass and things like that?
Well, part of it was the fact that we had a good idea of how to correct for glacial isostatic adjustment of the solid Earth, a gravity field. So that became a very crucial factor in being able to determine the mass balance of Antarctica. Not so much for Greenland, because Greenland was losing mass at such a tremendous rate that the gravity field that would be caused by post-glacial rebound there turned out to be at the 15% to 20% level, whereas for Antarctica, it was actually at the 100% level. So we had to really reduce the error bars on these glacial isostatic adjustment models for Antarctica. And so I was a participant in that modeling. That was my primary modeling effort.
Now, in all of this work, did this increase your interface with NASA, given NASA's overall interest in this area of research?
Yes, it did. So I became the lead of the ice mass balance intercomparison exercise for NASA, which was a combined effort with ESA.
Tell me about working with ESA and some of their different perspectives on the research.
I would say that ESA kind of uh, it's sort of interesting. We had a discussion in the cryosphere group about this 2 days ago. The ESA is sort of an interesting entity in and of itself, in that there are the British, and then there are the continental people, and the British uh, area of cryospheric sciences, and therefore determining mass balance. There are too many scientists and too little funding. So they're sometimes creating controversies among themselves that don't necessarily even have to be there. But the Europeans are a little bit more cold, calculated. They just want the measurement, and they're willing to live with the measurement. They don't invest their careers so much in what the result is. So the Europeans themselves actually form a good mixture of uh, straightforward science, I would say. The Americans were, and it may just depend upon the individuals that were there, are much more contentious and much more have tendency to fall into a position and then it's very difficult to move them out of that position. So it was a lot of personal dynamics that you had to bring together about 27 scientists who could all sit down at the same table and say, we are going to do inner comparisons of gravity, altimetry, and the mass flux method with the following set of rules. And we were able to do that. Between Andy Shepard and myself, we were able to pound out what those rules were and make sure that everyone followed them.
Erik, later on in the 2010s, as you started to think about the relationship between glacial melt and sea level rise, I'm curious if you thought about this as a uniform phenomenon or if different coastal areas would experience more flooding, would experience more land loss than other areas of the planet.
Yes, yeah, we certainly recognize that the ice sheets themselves contain a gravity field, and as that gravity field changes, the rates at which inundation will occur in some locations will be different than it will in other locations. One of the things that we did understand from research that had been done by Jerry Mitrovica's group was that the more intense sea level rise that would occur from the changes in the gravity field of Greenland and Antarctica could possibly be on both the western and eastern coasts of the United States, and also Japan. So you're talking about some of the most important industrialized part of the world being affected much more by sea level change than the rest of the world. So this preliminary estimate that was based upon rather crude models of Greenland and Antarctica heightened the interest in determining where the change in the environment was going to be the most. And of course, heat content of the Earth's oceans is also an important factor in this,
This,
and
ob-
circulation.
this obviously has international political ramifications for people who live on the coast and planning and things like that. Did you get involved in those political style conversations?
Yeah, I would say that I did not become so involved in the political conversations. I don't think that there have been many political conversations. I think the way this has worked out is that the NASA Sea Level team tries to inform people as well as we can of what is in store for them as the climate changes, and what communities might be most vulnerable so that they can make decisions about what they should do. For example, if you go to the eastern seaboard of the United States, where you have Chesapeake Bay and communities that are very vulnerable to storm phenomenon, you find that county to county there are different policies about what to do with sea level rise and coastal degradation. So it's really a coastal degradation problem. For example, there are some cities where storm surges actually enter the sewer system. And so their remedies depend upon a very local infrastructure. So becoming involved in the actual politics of what you should do to what the decisions that you should make, that's something we really want to stay away from. But we want people to understand that they have a resource that they can look at NASA data and NASA data sets that can be presented in a way that local decision makers can make decisions is the most important thing that we can do. We can have nothing to do with the local politics because local politics may have to do much with how much do people want to invest in infrastructural development as opposed to abandoning those coastal sites that they know are going to be inundated and be very costly to remain have infrastructure there.
Erik, of the many ways that your research has been honored and awarded, one I want to specifically ask you about is the NASA Exceptional Service Medal. What was it like when you got that, and what research were you being recognized for?
Yeah, I was being recognized, I think, for the work that I had done going back to the early 1990s, involving making predictions of what the geodetic responses would be of ice sheet retreat, and that many of these predictions had actually turned out to be proven by geodetic observations. So I think that's what the citation was for. And it was for the sustained research in that area.
Erik, moving in more recent years, as you reflected on the way that your research became somewhat even more interdisciplinary, did you see this as opportunity to meld the more recent cryospheric research with your earlier terrestrial geophysics research?
Yes, I did. Going back to the original convection code that I was asked to write at JPL that involved temperature-dependent viscosity, uh, because the um, because the mantle properties are strongly affected by temperature, and we know that a convective system has very large lateral variations in temperature. This means that the solid state properties of the minerals are going to be very different depending upon these changes in temperature. So, for example, Iceland is very near a mid-ocean ridge. So we know, or we infer that the temperature beneath Iceland is very much greater than it is between Scandinavia. So this means that the response time that we're going to have for glacial changes in Iceland is going to be very short. So the viscous response that we get from the mantle is going to have very large deformations over relatively short time spans, and that therefore we should be sensitive to the kind of changes that Iceland has experienced since the end of the Little Ice Age. And in fact, that's borne out.
Erik, I asked earlier about the road not taken not being a professor. More recently, you did have the opportunity to work with a few postdoctoral scholars. Tell me about
Mm-hmm.
that work and what you were able to accomplish.
Yeah, so I think it came at a very opportune time. Surendra Adhikari, who is trained as an engineer in Nepal, uh, became a glaciologist with some of the most eminent glacial modelers in the world, both in Belgium and in Canada. Came to JPL to do glacial modeling. But at the time, Eric Larue and I were interested in being able to do a more global model of sea level. And one of the things that we were interested in is being able to use the changes in the solid Earth um, as they might change the environment in which the ice was changing itself. So, in other words, to try to look at changes in the slope, for example, of the bottom topography beneath an ice sheet, as the ice sheet changed, because this is a feedback, and that feedback can be positive or it can be negative, meaning that the changes in the solid Earth can slow down or they can speed up the rate at which uh, mass exits the continent and goes into the oceans. So it turned out that Surendra Adhikari, this particular postdoc, was extraordinarily gifted and unintimidated by any higher order mathematics. So I realized at that point that he was probably capable of doing global geophysics. And so I, in various discussions, because we would have long discussions, I mentioned to that once he had written a computer code that did self-gravitation of the sea level in response to ice change, that he would be able to predict Earth rotation parameters. And he was very surprised. He says, how would I do that? I said, well, there's this thing called Euler's equations. And Euler's equations basically operate as a way of being able to take changes in the inertial tensor and then be able to drive the changes in the rotational properties of the Earth, the position of the pole, or the rate at which the planet's spinning. And I said, do you know that there's actually an extraordinarily good data set for the changes in the pole position of the Earth? And so he put two and two together, and he said, well, Euler's equations, those don't intimidate me, even if they're just a set of nonlinear ordinary differential equations in very low order. And so he set about both getting the data set and using Grace data, putting together a change in inertia tensor model for the Earth. And lo and behold, it matched the data. It matched the rotation data. Greatness of postdocs.
Erik, moving our story right up to the present, in what ways did COVID and the lockdown affect your research? And did it also influence the timing of your decision to retire?
It didn't. It did not influence the timing of of my retirement. My timing of my retirement is basically tied to the ages and joy I have of my grandchildren, and that's really what motivated me to retire. But one of the stories I tell about retirement is that I worked with Helen Cerusi at JPL, who was the ice modeler, and when we get together, my oldest granddaughter was getting older, and she was still looking very young. I was thinking, when a young person I work with at JPL who has a PhD starts looking like my granddaughter, then I know it's time to retire. So that became part of that story. But the COVID lockdown is kind of interesting because it put me in a position where I could do Zoom meetings, but Zoom meetings just aren't very much fun, and you don't really get in long conversations with people at Zoom meetings. It put me in a situation where every day, I could get up and I could continue doing mathematical analysis of advanced geodetic problems, and that's what I've done.
Well, Erik, now that we've worked right up to the present, for the last part of our talk, I'd like to ask a few retrospective questions about your career, and then we'll end looking to the future. So first, what value do you see having this duality in your research where you started, more in terrestrial geophysics and then you moved more into cryospheric research? In what ways have both aspects of your research agenda positively influenced the other?
Yeah. So I would say it is because it's this interface at the surface of the Earth. You have a stress that is forcing the deep interior of the Earth. I just came back from a workshop that we had at University of Minnesota, where we had all of the people that were involved in this project field project and interpretation, one of the things we want to try to understand is we want to understand the ongoing uplift of the region in response to mass change. And we had someone that came from another part of the geosciences department there who does experimental rock physics and creep. And he said, this is just the perfect laboratory that you have here. You have a great knowledge of how the ice is changing, and you have this unknown that is how the Earth is going to respond. And he says, I can't see a better laboratory that you would have. So that's how it affects solid Earth sciences. But I would say on the side of cryospheric sciences that you now have a full kind of Earth um, system science modeling capability in terms of you're able to model the gravity field of the Earth as the ice changes, and you know how that interaction can feed back to the ice model, and you also have an idea how you might be able to slow down ice loss or speed up ice loss, and so the two are interacting. So you're able to make contributions to cryospheric sciences and also to projections of future changes in the environment that we're going to experience as the phenomenon of global warming goes on.
Erik, of all the scientific research you've been involved in, what has been most satisfying in really making a discovery and changing the way we understand these processes?
I would say, in terms of discovery, I think it was the discovery that the GRACE science data set was so full of new information. I would say that was one of the most, and that the research that I do complements this new scientific frontier. I'd say that the data set was almost revolutionary to me in science.
Because JPL contributes more in analysis and observation and not in climate mitigation, where do you see other government agencies, other non-governmental organizations, how do they take all of this research actually to make us adapt and mitigate climate change?
Yeah, so I didn't know this interview was going to go so long because we have a scientist that I worked with at JPL was having a lunch together. And I'm perfectly happy to continue this interview and miss the lunch, which started at 11:30. But her name is Nicole Schlegel, and she is leaving JPL, leaving the Cryospheric Sciences Group, and she's going to NOAA, National Oceanographic and Atmospheric Administration. And she there is going to put together a new ice physics group that is going to try to help make projections of sea level change that are related to the cryosphere, because NOAA now understands that to be able to be a kind of a viable community serving organization, which is what they're calling is, they need someone who's capable of being able to do this kind of simulation. So that's the relationship, I think, between NASA science and the need to help the society protect itself from future changes in sea level.
Well, finally, Erik, last question looking to the future. As you explained, in the 1990s, JPL was not fully invested in earth science and climate change research. Now, obviously, it is. What are you most excited about? What accounts for this transition to JPL's investment, and where can it lead in the future?
Yeah, so I think that oddly enough, I mean, I see the capability to be able to monitor great details of the Earth system using NASA technology. The whole ecosystem can be monitored, I think, much more effectively, so that we can start to understand what kind of trends there are in really in our ability to be able to sustain food supply for a growing population. So I see new technologies, and it's always NASA that its calling is to develop those new technologies remote sensing technologies that will allow us to be able to determine, in fact, what are the time series that tell us where things are going in time so that we can inform agencies like NOAA about observational systems that they should put into climate forecasting and inform the entire international community of climate scientists.
Well, Eric, I want to thank you for spending this time with me. It's been a wonderful, wide ranging conversation. I'm so appreciative of your time. Thank you so much.